Imagine purchasing a state-of-the-art AI server, a machine promising petatops of raw processing power, designed to run the most advanced artificial intelligence models on Earth. You'd expect its expensive processing cores to be screaming, pushed to their absolute limit. But when you look closer, you find a paradox. Most of the time, these powerful processors are barely breaking a sweat. Their utilization sits in the single, maybe low double digits. They're effectively asleep, waiting. This isn't a software bug or a lack of demand. It's a fundamental physical bottleneck, known as the memory wall. Your supercomputer isn't bottlenecked by its ability to process data, but by its ability to get that data to where it needs to be. Think of it like this. Your processor is a Michelin star chef, incredibly fast and efficient. But their pantry, the memory, is a mile down the road. Every single ingredient they need has to be fetched by a runner, one at a time. The chef spends most of their time waiting, not cooking. This bottleneck isn't new. It's a legacy of how we've built computers for the past 80 years, a design known as the von Neumann architecture. When John von Neumann laid out this blueprint in the 1940s, it made perfect sense. Logic circuits were expensive, and memory was slow and small. Separating the processor from memory was an efficient way to reuse the same wiring for both instructions and data. It was the birth of the general-purpose computer. But what was once a sensible compromise has become, with the advent of AI, a profound limitation. This problem was even predicted decades ago, notably by researchers Wolf and McKee in their 1995 paper, Hitting the Memory Wall. For decades, the memory wall was noticeable, but manageable. Then came large language models. Suddenly, the amount of data needed for a single operation exploded. To predict just one word, a modern LLM might need to access every single weight from a model containing tens of billions, even hundreds of billions, of parameters. This introduces a concept called arithmetic intensity. Training an AI, teaching it new things, is often compute-bound, meaning you need raw processing power. But running an AI, making it generate text or images, known as inference, is overwhelmingly memory bandwidth bound. It's not about how fast your chef can chop. It's about how quickly they get new ingredients from that distant pantry. Why is moving data so slow? It's pure physics. Data travels as electrical signals. These signals have a speed limit, not just the speed of light, which itself slows down inside silicon, but also the resistance and capacitance of the wires. Even tiny distances on a circuit board become significant when you're talking about quadrillions of operations per second. The physical path from the main memory, often separate chips, to the processor cores, located elsewhere, involves traversing multiple layers of packaging, circuit traces, and connectors. Each millimeter of travel adds latency, degrading performance, and increasing power consumption. To overcome this, chip designers have been forced into radical new approaches. Enter high-bandwidth memory, or HBM. Instead of placing memory chips far away on a motherboard, HBM stacks multiple memory dies directly on top of each other. Think of it like a multi-story parking garage for data, right next to your chef's kitchen. These stacks are then placed on a special silicon layer called an interposer, sitting very close to the main processor. This 2.5D packaging shortens the data pathways dramatically, allowing for thousands of connections between memory and processor, creating a super-wide data highway. HBM3E, the current cutting edge, pushes incredible amounts of data. But even HBM3E isn't enough. The hunger for data is relentless. The next generation, HBM4, slated for 2026, is taking this concept even further. It's shifting from a 1024-bit to a massive 2048-bit interface. This means moving beyond 2.5D to true 3D integration. Instead of sitting side by side on an interposer, the HBM memory will be stacked directly on top of the logic die. Data will travel through thousands of microscopic vertical tunnels called through-silicon vias, or TSVs, literally burrowing through layers of silicon. It's like adding direct elevator shafts between every floor of that memory garage and the chef's kitchen below, minimizing travel distance to an unprecedented degree. This fundamental redesign of how data moves isn't just an engineering feat. It's reshaping the entire landscape of computing. It explains why AI inference remains stubbornly expensive consuming vast amounts of power just to move data around. It explains why startups and hyperscalers are exploring radical new architectures, from wafer-scale engines to processing and memory designs, all aimed at bringing computation closer to data. NVIDIA, long dominant in AI with its powerful GPUs, is now being challenged not just on raw processing power, but on its ability to integrate and package memory effectively. The race to AI isn't just about faster chips. It's about breaking down the invisible wall that chokes them.